All right, so we're starting our new unit, which is all about energy and work, because energy is the capacity to do some work measured in joules for us. Often energy in the United States is measured in calories, but because we're Canadian, we're on the metric system, which is joules. Now, there's several types of energy, such as radiant energy, which is the sun, nice heat. Sound energy, sound waves. Of course, nuclear energy, nuclear reactions happen. Chemical energy, like a set of matches. Thermal energy, it's heat. A lot of these that we're going to look into. Some of them we are, some of them we're not. But again, there's going to be a little project in our next unit where you can investigate some of these forms of energy. But for us, we're going to focus in on a few different types of energy. Now, like I said, energy is the capacity to do work. And so work is the energy transferred to an object when a force F acting on an object moves at a distance d. So again, we're kind of looking at our last unit with forces and how that relates to energy. Now, so in other words, with work, because that's where our focus is right now, it's the measurement basically of how far someone pushed or pulled an object, taking into account the magnitude of the force. All right, so there's a formula for work, and that formula is work is equal to force times distance. So again, let me write those down. Again, this is work, which is your ability to do convert energy, so that is in joules. All right, and again, our F value here is our force that's applied. And D is, well, your distance. So again, work, how much energy you've expended or changed something is based on how hard you have to push or pull and how far you moved it. All right, so on that note, let's try out a couple examples here. Mike uses 300 joules of energy while pushing a box across the floor. If he used a force of 65 newtons, how far did he move the box? All right, so again, as always, I like to write down my variables of what I have. And so that 300 joules of energy, that's how much work has been done. All right, 300 joules. We know that Mike here pushed with a force of 65 newtons. And this time we are looking for our distance. All right, so, well, obviously our formula today is work equals force times distance. So that's what we're going to use. All right, so I'm going to plug in my values. So again, work is 300. My force here was 65 newtons, and we're trying to find the distance. All right, well, I'm just going to get D by itself here. So I'm going to have to divide both sides by this 65. All right, and so those 65s divide each other out, and they're gone. And what we're left with is our distance here, which is 300 divided by 65. Let's see here, grab my calculator, go to 2 decimal places, and I get 4.62. And again, because we are in our standard units, we're looking at meters. So we moved it 4.62 meters. All right, let's try something a little bit different. Exam 2, while bench pressing 115 kilograms. It's a good bench, that's about 250. John moves the bar up 36 centimeters. How much work does he do if he does 1 rep or 10 reps? All right, so 1 rep refers to lifting that bar up once, and 10 reps refers to lifting that bar up 10 times. Now, here's the thing is that we have this weight. So again, a free body diagram, I just draw it as a block, which is great for me because I'm not very good with art. And then we got 115 kilograms. Now, when we are looking for the work, because that's what we're dealing with here. Whoops. All right, that's what we want to know is how much work is done. We know the distance it's moved. Now, we got a bit of a problem here because it's in centimeters, right? And that's not our standard unit. So again, to convert centimeters to meters, I have to divide by 100, and I end up with 0.36 meters. Well, that will get us in our standard units. Now, here's the thing is we have the mass. We need the force here. We don't have the force, right, to substitute into our formula. But here's the thing is that this weight pulls down with the force of gravity. So this is from our last unit here, which is Fg. And we can find that force by taking the mass times g, which again is our force of gravity. And so if I take my mass, which is the 115 kilograms, and I multiply it by g, which is our acceleration due to gravity, which is our 9.8. We end up with, let's see here. Oh, I actually get a round number. 1,127 newtons. Now, when this person here, what's his name? Mike? Oh, John. When John here moves the bar up, what he has to do is apply a force to counteract gravity. And so in this case, that Fa, the applied force, is going to be equal to your force of gravity. All right, and so our force here that we need to apply to lift this bar up is 1,127 newtons. All right, so now that I have the force, I can use that formula, which is work is equal to force times distance. So, of course, we had to figure some stuff out here first. All right, so work, again, our force here is 11,027 newtons. All right, our distance, again, in standard units is 0.36. And the amount of work done, or the amount of energy used, we can look at it two different ways. Let's see here, I multiply them out, and I get 405. Again, go to two decimal places, 7.2. And again, work is referring to how much energy was used up. And so we're talking about joules. All right. So, well, if that is 1 rep, 1 time lifting that bar up, 10 reps, well, all we're going to do is take our work and take that 405.72 joules that it takes for each repetition. And since we're doing 10 of them, I'm just going to multiply by 10. All right, and so well, that's only going to move the decimal place 1 to the right here. And so the amount of energy would be 4,057.2 joules. There we go. So again, we had to figure out the force of gravity, and to lift that bar up, you have to fight gravity. That's the whole part about weightlifting sometimes, or most of the time. Any questions so far? All right, let's see here. I think we got one more short lesson today. This one anyways. A cart is pushed at a constant velocity, a distance of 9 meters with a force of 20 newtons. Calculates the work done by friction. So again, this is tying into what we did last unit. So we got some object, a cart. Again, I just draw a box. All right, now it says that the force applied is 20 newtons. But the other thing is that we're looking for the work done by friction. All right, well, again, friction always works against you, our force of friction. And so I have to figure out what that force of friction is. But again, tying into last unit, constant velocity. What that means when you got a constant velocity is that your forces are balanced. And so if there's a force applied of 20 newtons going to the right, well, then it must be our force of friction is 20 newtons to the left. Now, here's the thing with your work this time out. It's going to be a little bit different. We're going to use the same formula here. The work is equal to force times distance. Now, here's, again, the distance this object's moving is to the right. but our friction is to the left. And so when I put this force in, I'm going to put a minus 20 in because it's going in the opposite direction. Now, when I have my distance here, let me see, I got 9 meters. Well, that's in our standard unit, so I'll put a 9 in here. All right. And again, I'm going to say it's, let's see here, negative as F, our force and our distance are in the opposite direction. That's terrible writing. I apologize. I should have just used the note. All right. So again, that's the reason I got the negative sign in there, is because F and D are in the opposite direction this time out. All right. And so now when I calculate it, I guess I got to go down here. Work, I got negative 20 times 9, and I end up with minus 180 joules. So it's actually negative work, because what's happening here is friction is working against us. Whoever's pushing this car, I should say. It's working against you, and so that means you now have negative work, which you can have. You can also have zero work. We're not going to get into that, but zero work is when you can travel a distance. Well, there's several scenarios, but one of the distances, you push a tree or push a house and it doesn't move. Well, your distance is 0. And so you actually are qualifying and saying that you did zero work, even though you pushed hard, you didn't move it anywhere. The other thing that can happen is if you have something floating in space, it's moving a distance, but there's no force on it. So no work is being done. So there is different situations when you can have zero work. But again, we're just worried about positive and negative work. All right, now